Today we have the pleasure of having Chenliang. He's an assistant professor at Rochester, University of Rochester. And he's going to be talking about multi-level alignment and audiovisual scene generation and learning. Thank you.
Thank you, Diego. Hello, everyone. It's my great pleasure to be here. And I know that this graphics lab in IMPA plays a major role in Brazilian visual computing. So I'm really honored to be here to give this talk. And also, I am very grateful for Diego and Luis for inviting me to here. My name is Chenliang Xu, and I am an associate professor of computer science at the University of Rochester. I can give you guys a little bit of background of University of Rochester. We are a small private allied school located in Western New York. It is about 1 hour to Buffalo, Niagara Falls, 3 hours to Toronto, and 5 hours to New York City. In Rochester, we have a very small campus, about less than 10,000 undergraduates, and we have a small department. Actually, all departments are small. In computer science, we have a faculty tenure track plus tenured professors are about 20, and including teaching faculty, the size is roughly under 30 faculty members. And we have a few people, like we are historically strong in AI, HCI, computer systems, and theory. In AI especially, we are strong in computer vision and natural language processing. Besides me, there are a couple of other faculty also on computer vision, machine learning, deep learning, data mining, natural language processing. Yeah. All right. So if you guys ever visited, Western New York, please let me know. Okay. Happy to, host you guys. So my, like I said, my group is mostly in computer vision and multimodal learning. But my talk today has a strong connection to visual computing. So I'm going to talk about how audio, visual, spatial, and semantic signals align. How do they align across different levels for scene understanding and scene generation? Okay. So this using of audiovisual is actually loosely inspired by how humans perceive the world. Like this human baby here, humans perceive the world primarily through 5 different senses. We have vision, hearing, touch, smell, and taste. And it's a collaborative effort of all different senses that contributes to the human perception of the world. Okay. Now, of all those 5 senses, hearing and vision are 2 dominant sense of human perception. So today, my talk is going to basically try to talk about different levels of the alignment between hearing and vision in terms of doing this scene understanding and generation. So one example is over there. We have this audiovisual scene understanding and generation. Just imagine this is in a room, and you have different sounding sources, placed over there, and they collectively makes a sound in this room environment. Inside of the audio tasks, you can do source separation to separate where is this sound coming from. Just like we do computer vision, we do segmentation. We wanted to segment the object, the shapes spatially. In audio domain, people are also interested in separating out different sound sources and their sound waves from this mixture of sound. And from a visual computing perspective, we are also interested in creating this 3D environment representation of this room. And there's an interesting connection between audio and the visual because how we perceive this audio actually reflects material properties, 3D geometry of the room, because those things are reflected in this audio reverberation. That indicative of the a lot of visual properties. Now, okay, so when I see this problem of alignment between audio and visual, I treat them as a spectrum of alignment from the coarse to the fine level. Okay? So at the very coarse level, maybe audio and visual are just loosely connected by say categorical labels or phrases. When we move to the middle level, okay, we are paying more attention to specific object instances. We wanted to preserve their acoustic characteristics and their visual characteristics. Okay? And even going to more finer grain, we have those geometry, material properties, complex scene setup, and visual motions that aligns in between visual and audio signals. Now, today I'm going to give you a couple of examples across this spectrum of alignment. At the very coarse level, we have this audio-visual sound separation. So the idea is that, given an audio mixture, and you have certain semantic indication, like a text string, text prompts, or even a visual image, and we can separate out this corresponding semantic object sound from this audio mixture. Now, in the middle level, we have this audio-visual editing. So the idea is that, given this input image and its audio, this is a mem is playing a violin. We wanted to modify this audio-visual example according to language prompts, like a dog is barking and playing. So you wanted to preserve, this is still a violin violin instruments, but now you have a dog playing, and preserve this original violin sound. Instead, you're adding a dog barking sound, creating a new mixture. Now, at the very fine level, we have this audio-visual acoustic synthesis, which is likely of most interesting to people here today who focus on visual computing. And I'm going to first, come into this fine topic, and which we call this audio-visual acoustic synthesis. Now, the goal for this is that we wanted to generate realistic binaural audio for any new position of a speaker and a listener within a visual scene. Okay. So there are a couple of things. First of all, we have this binaural audio. The binaural audio actually is like how we human perceive the sound. We have left and right channel with two L's, and how the sound arrives to our left and the right, there's actually a slight difference. And from that slight difference, you can actually compute, a rough distance where is the sound source to us. So there's a left and right channels difference that is very indicative signal to the sound source in the 3D environment. Okay. Now the input video, which is a recorded video here, that's going to be your input to the system. This is usually from certain fixed camera trajectory, shooting this indoor or even outdoor environment, having somebody like playing the sound. Now, the output is that we wanted to preserve those room geometry and material properties, while we can change the sounding sources and change the listener positions from a new camera trajectory. We want to create that realistic audiovisual experience. Okay? So sort of synthesize both the audio and the visual thing from a novel listener's perspective. Okay? And that is a task which are related to how sound propagates in this environment, reflects in this environment, and observed by the objects and the geometry in the scene. Okay. Now, to tackle this problem, we have developed a couple of methods over the years. So the first exploration is coming actually from these neural fields. And I'm sure you guys are familiar with this neural rendering fields, NERF. So this is actually back to 5 or 6 years ago. The idea is that we wanted to use a neural network, usually a multi-layer perceptron, to represent this 3D scene. And you can send those queries X, Y, Z, like the 3D location, and theta and phi are viewing angles of this 3D scene. And this neural network is going to output a color and the density over there. And everything is actually stored inside of a neural network. In the training, you are training this multi-layer perception, the neural networks, to remember this thing. Now, this is one example. We see here we have created a 3D thing from a static object over there. And over the years, people have pushed this idea to also create dynamic video things. Okay? And our goal here is to sort of extending the NERF idea to include audiovisual two modalities over there. Okay? So NERF is a visual primary pipeline. Our goal here is trying to do a audiovisual NERF. So before we talk about the method, so we always wanted to define the task a little bit, concrete, so what is the our goal here. Now, this is actually an open stage in Highland Park in the city of Rochester, and we placed a 360-degree speaker as our sound source at the middle of the stage. Okay? Now you can record different audiovisual experiences from different camera positions.
Real-world audiovisual scene synthesis task.
So this is observation 1. The camera is roughly positioned here, and this is what this camera sees. And obviously you just heard what is played at this position of the camera.
Real-world audiovisual scene synthesis task.
Okay, now this is a new position.
Real-world audiovisual scene synthesis task.
This is another position. Now our goal is that can we, based on those existing observations, and we generate for any given new camera poses inside of this 3D scene, what will it look like and what will it sound like? Okay. Now, concretely, now this comes to this definition. We have this given a static environment E and a multiple audiovisual observations O. Okay, and those observations consist of camera poses, source audio, target audio, and the image, right? And the output. Right here. So we also those are the camera poses and source audio. Okay. Now the output is given this observation environment, right? Now we have any given pose queries and the source audio, so you can change the audio to a different, song or different sound source, but still inside of this environment. Okay, and we wanted to generate those audiovisual corresponding experiences. Okay, over there. Now the method here is a visually conditioned audio nerve. Okay. So we still have a visual nerve. So this is actually like a two-stage process. We have a visual nerve. So given those position and direction, and we generate this and we train this visual nerve from a lot of those camera trajectories, and we can generate this 3D scene with the color and the density at the given position. And then we encode that, right, as a condition through this audio-visual map, encode them as a conditional input to a audio nerve. And this audio nerve is something very similar to this visual nerve, but it's more simpler. You can see here this audio nerve takes the position X and Y, doesn't take Z. We don't consider vertical differences, like we treat them as a planar plane. Okay, and we have a viewing direction that indicates how your head is positioned in this plane. Okay. Now we generate basically a mask. This mask is the mixture and the difference, and this mask is going to give any input audio. Okay, so this can be like a new a new song that is you playing from the speaker, or a new person is talking about with a different speech, and we can convolve over this input audio, and then we can generate this synthesized audio to be left and right channel. Okay, like I said before, so the reason to create this stereo sound is we wanted to correspond how people in a 3D environment perceive the direction of the sound. Okay. Now in the training, this still gets this supervision back to this visual nerve over there. Okay, so this is the setup for this nerve training. Essentially, this is a visual nerve plus a conditional input into a audio nerve to generate a sound masks.
So the audio is not an output of the network.
So it's the output are these masks, and the mask is going to convolve over the audio to generate this final output. Now, the reason we do this is because we don't want to, we want to have the flexibility to replace the sound with any music, for example. Okay, yeah. What is preserved in this audio nerve is the differences of the left and the right channel in terms of perceiver, like me, and a speaker, maybe somebody else in this environment, that kind of relationship. But that sound source they can replace with different speech. So essentially we created this room acoustic fields that can be reused in various different scenarios. Yeah. Yes.
Why do you not? Sorry.
Go ahead.
Not consider the position Z? Is it because just to simplify the problem?
Yes, exactly. We simplify this problem primarily because here how we going to collect the data. The students using this device, which is a GoPro camera, 360-degree lens, and this binaural microphone, which has like a human L shape, right? So this is really sort of accurate in terms of like how human perceive the sound by modeling, the L shape. And this is a portable recorder, and this is a omnidirectional LG speaker, Bluetooth speaker is used as the sound source, and we place it at different locations in the lab, in classroom, outside in the park, and the student is holding this device, right, to record them. So for the sake of simplicity, we don't want them, hold high, hold down, so we omit that Z direction. Yeah. Yes.
What about the direction you're looking at? The sound, the synthesized sound has the property of rendering the right sound for the direction we're looking at?
Yeah. It does have, yes. So that is, this complicated setup is to capture this left and the right channel. So it is really good in terms, capturing that difference. I'm not sure if you can, do it with a normal. like from.
The slides, the equation doesn't have like the angle you're looking at the sound.
Here, here, yeah. The source position.
You mentioned you could change the position.
Yeah, you could change the position. Yes, that's a good question.
I guess it's the same way that you do image, because like you put there, you know, you have an image, right? So
you have an image over there.
so
Yeah.
You have the audio, right? So audio 360, then the angle. In the direction of the source, not
Yeah, it's actually fixed. It's fixed over there. So the location of the sound is fixed over there. Yeah. Yeah, so you will see like later on here, I'm going to show you one example. So this is in the lab, and the sound source is right here. So this is actually fixed. But what you mentioned is something I think we can explore in the future, right? How can we like move these sound sources? But I do have later example. But over there, I think maybe you need to retrain this whole field, which could be like potentially modeled into the input as well. Now those blue triangles are the cameras. Okay, so those are the recorded training cameras. And you see this method, it needs a lot of those partitions in this environment. And this red one is this generated new partition. And I'm going to play this video, and you can see that left and right channel, those are the audio over there. Sound source is right here. So this is, the camera is looking at here. Maybe this is the field of view. Sound source is right here. And this is the image you will see. Down on the bench and start to watch all the people walking by. I see all the different kind of faces, people all around the place, and wondering why I just smile. Right. So it's I'm not sure if you guys over there can listen, perceive the difference, but what they computed is there are indeed certain differences of left and right channel, and obviously from the the sound, when we move closer and move far, you perceive the difference, right? Now this is another example. So this is actually a larger 3D scene. It's inside of a house, and the sound source is placed in the living room. And we will show you a trajectory coming from the living room, go to the kitchen. Okay. So now the same environment, but we change this sound source to here, and you can place any kind of song you like, right? Yeah. Now, this is another example. So this one is in this open environment. Now, this is outdoor in a park.
Real-world audiovisual scene synthesis task. 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 Real-world audiovisual scene synthesis task.
Yeah. So now that is our first exploration, and obviously, the sound is good, but you see it needs to be trained with a lot of camera poses, right? So there is actually a big trade-off in this state-of-the-art methods pursuing this direction. In general, there are two lines of methods. Our AV nerve is from the second one. So this is a vision-informed neural rendering. It produces realistic audio for those scene data, but fails to generalize. So for a given scene, you need a lot of sampling in order to train a good, realistic environment, because all it does is to do those interpretations of existing camera trajectory. Now, there is another method, which is a geometry-based audio simulation. So the idea over there is they create this 3D room environment, and they can shoot different sound rays to mimic those audio simulation. So this method generalizes well as long as it captures this 3D structure of the room, and from the simulation they can generate like any partition in this room. But the drawback is that it lacks the realism, because they don't capture those material properties. They don't capture existing sound noises in this room. For example, this machine here, it's some sound over there, but if you don't collect a real example in this room, you don't know. Okay. Now, our second hypothesis, second exploration, is to see whether we can leverage those, explicit physical priors in this audiovisual modeling to bridge this gap between, generalization and realism. Okay, so now this comes to this second exploration, which we call a physics integrated audiovisual acoustic synthesis. Okay, now this is our pipeline. This is a two-stage pipeline. It combines this geometry-based audio simulation and vision-informed neural rendering. Okay, now in this geometry-based audio simulation, bad realism, good generalization; neural network-based, good realization, bad generalization. And what we want to achieve is the best of both worlds. Okay, so this is actually a two-stage pipeline. So the first stage is we have a vision-guided audio simulation. Okay, so the idea is that we have those camera trajectory, capture this room data, and from there we're going to do a couple of process of environment creation that includes a 3D reconstruction of this room. You can do it either through nerve or through Gaussian splatting. And then we do those point cloud estimation of this room. After that, we do those mesh generation through this surface reconstruction. So you created a 3D environment like this. Okay. Now, the second step is what we are leveraging those audio simulation. Basically, we use those 3D meshes of this room, right? We can define this physical space and how this sound can travel over there, okay? And now this sound is treated as a collection of rays emitted from a source, and those simulation basically traces how those rays, as they interact with this scene's geometry, bumping from the world, different structures, eventually arrive at this perceiver partition as a collection of both direct and indirect passes, of those listener of those rays collected at the listener partition. So a lot of simulation carried it over there. Okay. Now we also calculated those impulse response, which related to the room geometry, reverberation, with those accumulated energy and head-related transfer function. Because still we wanted to know how your head is faces in this room in order to create these binaural channels. Okay. Now this has a strong generalization to novel sound sources and the listener partitions, because everything being done over there is through a simulation. Okay. Now, the step 2 basically is we trying to use this a refinement network, okay, to fix those realism problem. Okay, this sound geometry based sound simulation, good generalization, bad realism, because there's a big gap in accurate material properties, computational limitations by simulating those rays. Those are very expensive, and other unmodeled effects of the room, like what I mentioned. There are background noises in that room, maybe coming from the AC, coming from audio recordings, or various different, room characteristics, sound characteristics. Those are not at all modeled in these first physical simulations. And we wanted to fix them here. Now, the stage 2 is a audio refinement network with flow matching, and we use a neural network-based method to bridge this gap. Okay, there are in general 2 model choices. So we can do one is a regression-based method, deterministic models, just predicts what those numbers are directly, or we can do in a generative fashion, which is learn those underlying probabilistic distribution by modeling it as a generative model. And we found this generative model leads to higher fidelity and more diverse sound that is preferred over those regression method. And then in terms of the method, we have experimented this diffusion models versus flow matching models. Now, in general, this flow matching model is the way to go because this gets your simpler, more efficient training, much faster inference with fewer steps. Okay, so the idea over there is we have a sound source, which is any kind of music you wanted to play. Okay, those are the raw audio file. And if this speaker in that room, right, is this raw audio file, you would expect certain ground truth sound, which is realistically collected over there in this room. Now, your input to this flow matching algorithm is your simulated sound, which is through this physical simulation. Okay, so this is your starting point is the simulated sound, and through this intermediate sound, like different steps, we wanted to go to this ground truth sound, and this audio refinement network is basically to bridge this gap in between this simulated sound to this ground truth sound, given any sound source.
How do you use the geometry of the space, point cloud or the mesh, or is it fixed?
So right now in this second stage, you don't use that at all. Okay, so
the geometry is fixed.
This geometry is fixed. It's still inside of that room. By the training, you can see this network is a pure audio-based training. Like input is a simulated sound, output is your predicted sound that mimics this ground truth sound.
Yeah, but you could condition the flow matching.
Right,
using the point cloud or the
you could still do that. Yes. So. Yeah, exactly. Yeah, exactly. Now, this is the network. We do this, but we didn't consider that. But that could be like a future direction we could explore. So here, this is sample sound, source sound, and everything here is through a basically like an acoustic refinement network to achieve the job. Yeah. So now we're going to evaluate this work. Now this becomes the focus of this evaluation becomes to see how your method can generalize to unseen sound source prediction within the same environment. Now, how we're going to evaluate it is we're still going to use the same data set we collected before for the first exploration, But right now, in the training, we only give our algorithm one video per environment. Okay, so just one pass of this environment, so which is much reduced from the first one. And all remaining videos collected in this environment are be used for the evaluation to measure the quality. Okay. So the same here. So we have office, house, apartment, outdoor, same as before, but with much fewer training trajectories. And this is like a evaluation. This is the pi AVAS is this method here, and across the board, this gets much better performance. I won't go into the detail of those metrics, but the lower the better in terms of measuring the sound quality. AV-nerve is the previous method we have came up, and this pi AVAS is evaluated in this new setup, gets much better performance. Okay, in terms of the speed, this is a slightly higher than the AV-nerve, but it still meets this real-time requirement. Now, we also evaluated the first stage, which is this vision-guided audio simulation. And we try to use it as a plug-and-play model into a couple of different methods, including the previous AV-nerve. And that also shows performance improvement across the board. Okay. So two-stage, and just use the first one as plug-and-play. Now, here is some examples. Okay. Let's see. So this is the office setup, right? And we have a sound source positioned here. This is the camera, and you won't see it actually from this perceived image because for vision we always have a FOV over there, but audio is actually 360 degree. We hear like surrounding sound. Now this is the input audio. So this is the raw audio file that we send to the speaker. And this is the simulated sound by just looking at this geometry of the room, how this sound is going to be perceived if we simply, put the audio file over there and the listener is here, head direction facing this angle. Okay, and this is ground truth. This is our predicted sound. Right. So it basically brings this simulated sound closer to ground truth. Yeah, a little bit closer. And this is another example inside of a house. One input is audio. Right. Input audio is always crystal clear because they are raw audio file. Now the ground truth. Okay. Simulation. Right. And yeah, so this is also like looking at this potential. I don't know why they don't look at the sound source.
So you start from the input audio and then you iterate on formatting.
We actually started from the simulated audio. Yes, iteratively through this refinement, we get this predicted audio. So actually, the simulated audio. So how we from here, the input audio to the simulated audio is through this stage one physics simulation of the room structure. Okay, so that gives you from here to here, first stage. Okay, and the second stage gives you from the simulated sound to this predicted sound. Yeah, that's through the audio refinement network, two-stage pipeline. Yeah.
I wonder, like,
yeah.
if you have like any other restriction, for example, some new jump, some modification of the jump, if you could use diffusion, DPS, diffusion posterior sampling, that you could drift a little bit the integration of flow mesh to match.
Oh yes. I think one good usefulness for that is what if I just move the sofa to a different position in the room, right? Yes, and I don't want to retrain the network. Yeah, how can we modify things over there? That's a very good angle. Yes, yeah, yeah, it would be interesting. Yeah, nice. Yeah, future work. Yeah. Okay. So now this basically gives us this fine level alignment between audio and vision. You see they are coupled at the 3D thing, a lot of fun details, material things, geometry. Now on the other side, other end of the spectrum, we have this very coarse level matching, that is the visually informed audio separation. Okay, so this is what we have achieved is a audio separation network essentially. This is a paper published at ACCV 2 years ago and got the best paper runner-up. And then a improved paper was published in IGCV earlier this year or last year. And this is kind of the first method that is using this diffusion-based method for sound separation. So previous methods are all using mask prediction to predict those masks and convolve over the original sound to produce sound separation. Those are, most of them are deterministic modeling. Now here, this is the first work that is we see using a generative model, like a diffusion model, that to generate those separated sound directly by giving those mixture of the sound and starting from a bunch of random signals, and we get those sound separation. And as a result is a very high quality sound separation that is across the board much better than those regression-based method. Because those regression-based method, they produce sound masks and eventually convolve over those mixture and get the results. And the information is always going to be less than perfect. Okay. Now with this diffusion method, you can sometimes even get better sound qualities than those mixture, because generative models nowadays are crazy. They can do a lot of interesting things. So here, this is a vision-informed method, meaning that we have a visual condition. We use this video. This guy is playing a musical instruments, and we have a short video clip, and we encode this short video clip, and through the transformer, use them as a condition input into this diffusion model. So in your mixture separation, we want to separate the sound that is corresponds to your visual input. If you change this visual to maybe a running car or a different type of objects, this is going to be a different sound separation according to that visual input. Now this is a mixture with two types of visual conditions over probably 1,000 iteration, and eventually gets you those separated sound from the mixture. Now here I'm going to show you some examples. This is a input mixture. Okay, so there are, I heard at least 3 different sounds over there, right? Now, we show you condition on the first. This is a bird image with a sound separation. Okay, and this is a gibbon image. Still, some of the child playing over there, but at least I think the bird sound is kind of separated out from it. This is another one, input mixture. Okay, so now here, this is fire truck serial. And helicopter. Now this is another one. This is actually a rat is biting this steel pole over there. Now, we kind of, so, yeah, go ahead.
Is there anything in the model that kind of verifies if there's any correlation between the things that were separated? If, for instance, if we join them together, we get back the mixture model. The mixture.
Oh, yeah. So now the diffusion model's goal is we do not do that. In this regression-based method, when you separate them, you add them back, they should be the original sound mixture. But in the diffusion model, there's no guarantee you have that, which is a good thing, because it can enhance the sound that is better than the original sound. Yeah. But that's a good question. Like all those regression-based methods are doing that. Okay. But the diffusion-based method, we don't do that. Models can generate. Maybe those sounds were constrained in your original input that you didn't collect them well, but you actually generated them. Yeah.
During training, the separation. This kind of method in diffusion models.
So the diffusion models is during the training you create those sound mixtures.
Okay.
Yeah. So you have any two sound mixtures, you create them together and use diffusion model to separate them out. Mm-hmm. Yeah. In other words, actually, those training is essentially free. No human labeling is needed over there. Yeah, it's totally unsupervised. You just sample any two to do a mixture, or even three. You can do that. Yeah. Now, what we also experimented with this sound separation is that we say, what if we can actually encode this into a chat, like, instead of providing the image, because seems like to us, this alignment between vision and audio is only happen at the categorical level. You can pursue like even fine grained separation that maybe two people are playing the violin at the same time, and you wanted to separate the violin sound of individual person. That is even harder task. But here, we didn't do that. It's simply you get a semantic meaning from the image, and this separation network seems just using that to separate the sound. So now we say, okay, so why don't we just use a text prompt to do that? Okay, we can feature that maybe into a chat, like people can interact with our system by just chatting with the system. I want a fruit sound being separated from this sound mixture. Now we can extract this as a text prompts, and through clip model, which establish a connection between image and the text, we can use this encoding information to sort of as a condition to this sound separation. So we don't require, in the training we use those images, but in the test time we can use these text prompts and use the corresponding clip embedding of the image encoder of the text, insert them into as a conditional input to our sound separation, and that also worked. So you can do a sound separation with just a text input. So let me just show you one example. A motorcycle is so far, and you have the text prompts of a sofa. And a motorcycle. Yeah, so they are also very nicely being separated, but in the training, it's never been seen for those text prompts. Okay, so which means that this alignment between vision and audio isn't very strongly coupled over there. Okay. Now we even pursue this idea further. Now this Davis network requires this task-specific training, so it needs to do still training. It still needs training. Okay, and depends on, because it needs to be trained. So we need to talk about the generalization. If you train on larger scale, yes, they can do good generalization. But if you train, on limited examples, and you want to, the network never heard about maybe a truck sound, this is going to be very hard for it to generalize if you wanted to separate the truck sound. Now, at the same time, we see, those GPT or many, language tasks, we can essentially, enable sort of free, tasks in a lot of those language models, like GPT. GPT was never trained for, let's say, in natural language, like entity identification or other specific natural language tasks. It was trained for predicting the next token, and magically, through this kind of training, it does all kinds of natural language tasks as well, right? So what if we can take a large scale audio foundation model that is trained between language and audio, serving as a general like foundation model? Can we somehow enable this free separation capability from this foundational model? Okay, so this is a paper from last year's New Reps that the paper name is called Zero Sep. Essentially we can separate anything in a video, in a audio with zero training. So by just playing with a audio language foundation model. So here I'm just to show you a demo. Audio input. Now process this audio. And I suppose it's going to do like the separation. Like the network is never trained for audio separation, but taking a foundational audio language model. La voce è proprio simile a quella di by condition on the text input. Okay, so just separate this man speaking. So this is through.
Nobody is going to give you anything that you have not earned. Nobody cares how tough your upbringing
Now this is
was.
the video input. Similarly, this can deal with the video by the data tag actually taking those visual streams, it's taking those audio streams. But conditioned on this Obama picture.
Nobody cares how tough your upbringing was.
Yeah. So that is a little experiment we did over there. The separation quality isn't, state of the art, but it does show there's capability for you to, achieve like a zero step from a foundational audio language model by just feeding it with certain semantic information. Okay. Now coming to the middle, okay, so this could be like an interesting mixed field, like between the fine-grained 3D understanding and also the categorical separation. So this is maybe certain learning is happening. We wanted to preserve those object characteristics. Now this task is what we call natural language guided joint editing of audiovisual content. So the idea is that now we give a input image here and a corresponding sound, a bird is chirping, and we have those language prompts. A bird is chirping in the rain, a bird is chirping underwater, and we want to preserve those acoustic and vision characteristics of this bird, but place that on a different language prompt and generate the content. Okay? So these are the generated content. I'm going to, maybe, I guess nobody have ever heard like a bird is chirping underwater. I bet that. So, okay, so here, this is the bird is chirping, right? Now, under this language prompt, I would say like the similar kind of bird. You guys are in real, you are the experts of those birds. Under the rain. Now, excited? Under the water. Yes. Yeah, that's some interesting stupid thing like we did. Okay. Now, but in order to do this kind of task, there are still something we need to consider. First, we wanted to sort of preserve the characteristics of the input, like visual characteristics and acoustic characteristics, like on the matching thing over there. So you need to do like having certain kind of analysis understanding of what is correspondence over there. Multimodal consistency. After this edited audio and vision, this is the same bird and having the same kind of sound. Also, we wanted to reflect the user's editing requirements. So even a stupid request, we wanted to generate, that example to kind of match that. Okay. And in terms of the method, so this is a kind of a latent diffusion-based one-shot adaptation method. I think this is kind of a trendy thing. Maybe in CVPR 2 years ago, there's like a best paper about customizing like a diffusion model like into generate like customized things or something like that. Now we take the similar idea. So the goal is we wanted to achieve that 3 properties like I listed before. Now in the training, we are given this one image and it's mixed, the audio file, and we encode them through this clip model, which builds this contrastive learning between language and the image. Similarly, we have this clap model, which is a pre-trained, audio and language contrastive learning network. So they project them into the similar token space, embedding space, okay? And through this few layer of multi-layer perceptual, and we encode them together with those original text token. A telephone is ringing, and we use them as these conditions to this diffusion model, and generate this original content, sort of recovering this original thing. So the idea is that, in this training, we train just with this one example. And this text to image, text to audio are two diffusion network. We train many, many times and let these two networks sort of very much overfitted to this original example, but also paying attention to those language tokens description. Now in the inference time, everything is frozen. So with except you change this text tokenizer to include this new text condition, and through this fixed diffusion network, we're going to generate those characteristics. So idea is that the previous three property, the content fidelity, multimodal consistency, prompt faithfulness, are all being captured in this jointly trained diffusion network over there during this one-shot adaptation. Okay, and at the inference time, you can deal it with any other language prompts. So with this, the original input modified with language prompts, so get the final output. Okay, simple method.
So you are concatenating the encoding of the images and audio?
So this is actually mixed together. So this is mixed together through multi-layer perception. So so right now this is kind of like fused tokens already. Yeah, fused tokens through multi-layer perception. You really can't tell like which one is pure audio, which one is pure vision.
So no cross attention there. Just like you are just concatenating the tokens.
Concatenating the tokens, but through the multi-layer perception. Yeah. No attention. I guess you can replace attention with multi-layer perception over there. That can potentially also be able to do it. So then you have this language token, right? So now at this stage you have vision, audio, language, everything together, and they are all being sort of projected into this language space. Okay. After that, right? So it goes that as a textual condition to generate the original example. So this is the data set we created. It consists of 44 distinct sounding events from a couple of data sets. There are music data sets, there are speech data sets, VGG sound, which is more type of general YouTube type of data set. The events are animals, vehicles, tools, natural phenomenon, musical instruments, human speech. Okay. Now we also construct different scenarios because we want to evaluate it. So these are the language prompts. We have two sorts of language prompts. One is you can add a new object. This is a image or a recording of a certain thing with a dog barking, with a child laughing, like adding a new object editing through them. Or you can alter the environment. This is to keep the original language prompt, but you place them into an entirely different visual scenario, okay, background scenario over there. So this is the first example I have showed you. Now this is a person is speaking, and we say this person is speaking on a beach or by a crackling fireplace. And we want to preserve the visual and acoustic property of this person. Okay, so that's the
when we're back with a smile that reassures us that we're safe and loved in this world.
Okay, now just imagine you can place this lady here and his voice, but entirely into a different scene on a Copacabana beach, for example.
When we're back with a smile that reassures us that we're safe in this world.
Now,
when we're back with a smile that reassures us that we're safe and loved world.
and this is another example. A person is playing guitar. By the crowd.
So now it's look like you can generate like longer videos than before, right? Not video, audio than before.
Longer videos, yeah, maybe, yeah. So I heard.
The audio is longer than the
Yes, that's. I love the setup here. That's the first time like I actually heard like a little bit longer. I think either this is like maybe a afterward editing error, or actually the network is actually doing something amazing. Yeah, I have to investigate that a little bit more, but with those diffusion model, I think it's they're crazily capable. Yeah. So that also kind of seems like it's going to be like being used for creating like fake content, right? You have delivering the same speech, but I can change the background entirely. Yeah. Now let's see. So yeah, so this is room acoustic adjustments inside of small room, and for this a large cathedral. The same person, but under different rooms, and then the audio spectrums is listed over there. Let's see if the video can be. Yeah. Okay. So yeah, I can play them.
Today I'm going to do the well-awaited What's Going On with All Things Hair video part 2. So if you guys saw the first video.
So this is kind of like in a small room, like kind of like a studio quality, right? Now let's say sorry, it's a studio quality. Now this is in a small room.
And if you felt for the wedding always you one on the wall owning hair. Wow. So let us start the first video.
I can hear like this reverberation over there. I can think this is maybe not a studio recorded. Now this is in a large cathedral. This is very obvious. Yeah. So and the point is that you're going to generate those acoustically and visually matching thing in that environment. We didn't generate like a 3D thing. We just generated this, one background image. But presumably, you can generate 3D thing that will be like even more interesting, perhaps in the future.
And the only condition is is the image.
The text. Conditions are, well, I would say the conditions are the input audiovisual data and being respectful to your new language prompts.
So you kind of know more or less the geometry because it
More or less knows the geometry, but only loosely from the language prompts. Yeah.
Sorry, the input audio-visual data is an actual video, or is it just audio and just one image?
Just one image right now, just one image. Yeah. All right, so this is another example. So now we're gonna remember we have two types of prompts. So this type of prompts is to replace the object. Okay, this is the original example. Now here is this one. I can only say the network has good imaginations. Now replace with a child is laughing and playing, same violin. Yeah. All right, so now simply to conclude this talk, I've talked about different levels of this alignment and different tasks, audiovisual tasks require different levels of the alignment. And you can actually also solve a task in multiple levels of alignment. For example, you can solve sound separation. Right now, we just pay attention to categorical labels, but you can actually separate two different persons playing violins together, and in that case, you would need to go more detailed to those object identities and characteristics. Similarly, like other tasks, they can be solved at the different levels of the spectrum. Now, from a computer vision perspective, this cost to median level alignment focuses kind of more on the semantics part of vision and learning, while this fine level more focused on this measurements, visual geometry kind of things. Now, perhaps a question that we can ask along this line is how far can we push the learning of a audiovisual foundation or audiovisual language foundation model, right, in this spectrum of alignment. Right now, all those foundation models are kind of being learned at a very coarse level. They're being just matching those languages, categorical labels with their visual presentations. And perhaps going forward, can we actually learn those foundation models into those fine levels in this alignment spectrum? Okay. So with that, so finally, those are the two students that contributed a lot to this presentation. Chao is, just graduated, this month. Actually, I hooded him. This month, he is going to join Tencent 10 Yuan team to build their 10 Yuan large foundation model. And Susan is still with me. So those are the two primary student contributors to this work. And for my own group, I have other 4 PhD students. So yeah, we are a group of 5 or 6 PhD students. With that, thank you, and I would like to take any questions you have. Yeah. Okay. Yeah.
I was thinking about the first part of the presentation in which we were talking about binaural audio, right?
Yeah.
Can walk through a scene and have this synthesization of the audio across the scene.
Yes.
And I was thinking about kind of the inverse problem. What if we had information about a video of a scene with its audio, and we wanted to retrieve some sort of very clean and very I don't know, from what would be the fixed source?
Yeah.
Audio.
Yeah. So yeah, that's a good question. So yeah, like you were thinking about the reverse problem. How can we go from those perceived sound and we trace back to its clean audio file?
Recordings of live concerts.
Live concerts,
they
yes.
have like very bad and very dispersed recordings.
Mm.
You want to have some, for instance, a very good quality of what would be the sound very close to the performer's mouth.
Yes. That's a good one. I think it needs to do a couple of things. First, there's sound separation, obviously. In a concert, there are a lot of crowds, right, and a lot of different sounds, and you want to do sound separation over there, and then you wanted to somehow like retrieve the clean audio, studio quality audio that could be like potentially used with a like a audio you remember the audio refinement network, right? I can foresee there will be certain similar network but trained in a reverse fashion from those bad quality audio. How can we recover to clean audio, better audio quality? Yeah. um, I'm sure there are works over there. Yeah. Interesting. Yeah. um, Yeah, I think there are definitely works over there for acoustic hardcore person over there. But for vision people, I think we are more interested in this for word process that we wanted to position the sound inside of this 3D environment. Yeah, but it's a very good question. For the reverse way, how can the vision being used over there? Right.
If nobody has any more questions, I'm going to keep asking questions.
Yeah, show me.
I was also thinking about the first part of the presentation in which you had to again this task, and you had the two channels.
Yeah.
Of left and right noise.
Yes.
And I noticed that in the examples that you gave, they were mostly not very different from one another, the results. Are there any examples, for instance, in which you try, for instance, to put one ear of the ear in quotes of the machine that you use to capture sound very close to the the source?
Yeah.
Because then the different channels would, would have very different results. No?
So it's our brains are very remarkable. It captures those slight differences between left and right very accurately, and from that slight differences, they can tell whether this sounding objects is from which direction. Yeah. So it doesn't have like to be drastically different. So that slight difference is what you need in order to tell where the speaker is coming from. So you can imagine close your eye and I speak at this location and what I'm speaking over there. There's just a subtle differences between left and right, and from there you can actually know where am I speaking in terms of your position, whether I'm in front of you or back of you, left and right. Those rubber location you can tell very clearly. So that is the reason, despite that you see the differences the small, but if you enable the stereo sound, you can actually perceive the sound location where it comes from.
Maybe I missed these first modules. So you can give the input, the audio that you want to play. So when you're in the data they use to train the models, do you sample different sounds in order to be able to do this?
The first one, the first room geometry, right? Acoustic synthesis. In the training, you not necessary to play different sound. It's the, what you are calculating is a differences between left and right, and that is related to where you are standing in that room, and how you are facing this audio structure. For the first work, and for the second work over there, yes, you do need to sample a few little sound, because the room property needs to be learned. Okay, but it can be learned from one example, and it can also be learned from multiple example. Okay, but the refinement network, does just learn those room constants that cross different sounds. So, in other words, not necessary. You need to play in the training. You need to play different sounds. You can learn with one example or a couple of examples. That's enough. Yeah.
Yeah. I was also considering about sorry, I forgot the name of your model, Pi.
Pi AVAS. Yeah.
Pi AVAS. You first have a first module in which you have the physics simulation.
Yes.
And a second module in which you use the image condition, right?
Well, we didn't use image condition. That's the question Diag asked. We could use, but over there we didn't use.
Okay, so it's just diffusion on given the simulation as. I was considering, and I think I already know more or less why would nobody do what I suggest, but I was considering the idea of maybe trying to include learning into the properties of the materials within the simulation. So right now you just use physics and you try to learn how the sound propagates.
Yeah, more or less the room geometries. What? Yeah, more or less the primarily room geometries.
Yes.
Yeah.
So without consideration for the materials.
Yes.
But could instead of having a second module in which you use diffusion to add realism, couldn't you, for instance, try to learn the properties of each material in the scene to add realism in the physics simulation? You
could, yeah. You could, but other factors, for example, that is a physics simulation is very expensive. That is one. You cannot bypass that. Two, there are sounds that are specifically inherent to that room. Like this audio recording machine, which is having contribute to the background sound in this room. Or maybe like a running AC of that room. So those things are not learnable, in physics-based thing without any consideration to the room acoustic at all. Yeah.
Okay. So let's close the. Thank you very much. It was a wonderful talk.
Yeah. Thank you so much for inviting me. It's really an honor.
So.
Thank you, guys. Yeah.